Hello everyone! It's a pleasure to be here with you today and to have the opportunity to share this work. I'm going to present the project titled Implementation of a Solar Concentrator for Fruit Dehydrator. My name is Monica Colunga Saucedo. I'm a PhD student at the Institute of Physics at the Autonomous University of San Luis Potosí in Mexico. In this project, I'll talk about the design of construction of an indirect type solar dehydrator. The structure is built with 1-inch aluminum profiles covered with food-grade aluminum sheet, and it has a polycarbonate cover. It has a drying chamber with a volume of 0.65 cubic meters equipped with stainless steel mesh trays and a heat exchanger underneath. This exchanger is connected via a pump to a 1 square meter array of asymmetric cylindrical mirrors oriented to west to east and facing south, with a concentration factor of 3 suns. At the focal point of the concentrators, copper pipes were placed, covered with fins made of an absorbent material that helps capture and transfer solar energy to the heat transfer fluid. Here you can see a real image of the prototype, and in this video a 3D design made with SketchUp. The red marks inside the dehydrator indicate the locations of the sensors we use to measure temperature and humidity during the drying process. At the bottom of the system are the heat exchanger, which transfers the thermal energy from the fluid to the air, the chimney, which allows the controlled release of the water vapor, and the piping system, which connects the pump to the storage tank and then to the solar concentrators. The circuit then loops back to the exchanger, completing the closed-loop flow. This type of configuration, being a closed system, has an important advantage. It minimizes the loss of volatile compounds in the food, helping to better preserve their properties and resulting in a higher quality final product. This slide shows a simulator made using the ray tracing software Tonatiuh, which helps visualize how many solar rays are absorbed by the system's heat-absorbing fins. The design was specifically created for the geographic location of San Luis Potosí, which is at 23 degrees latitude. The aim was for the flat section of the asymmetric cylindrical concentrator to capture as much solar radiation as possible without needing a tracking system. The simulation shows that the highest energy capture happens during the summer solstice, when the sun's rays are more direct. In contrast, during the winter solstice, there is a noticeable drop in captured radiation due to the lower sun angle. However, this reduction is balanced by a key benefit: energy and maintenance savings, since the system doesn't need to adjust its orientation throughout the year. In short, we sacrifice a bit of energy in winter, but we gain a simplicity and operational efficiency. To test the system performance, we carry out a dehydration trial using apples. We place 2.1 kilograms of apple slices, each about 5 millimeters thick, on 3 trays spaced 8 centimeters apart. The apples remain inside the dehydrator for 48 hours. At the end of the process, we obtain a bit more than half a kilogram of dried apples, with a water activity of 0.35 sustainable of preservation. During the drying process, the temperature of the heat transfer fluid inside the exchanger reached up to 80 degrees Celsius, while the temperature inside the drying chamber reached 58 degrees Celsius. The relative humidity inside the chamber dropped as low as 20%, which helped extract moistures from the product efficiently. We also ran drying curve tests with different fruits cut into small pieces to analyze how they behave during dehydration. To do this, the samples were weighed at the beginning and the end of the process. In general, we found that most fruits reach a good level of dehydration after about 26 hours of exposure, which is equivalent to roughly 12 effective solar hours. These results help us understand the optimal drying time depending on the type and the size of the fruit, allowing us to fine-tune the process for a good balance between energy efficiency and product quality. Now, Regarding of the efficiency of the prototype. In the graph shown here, you can see the instantaneous thermal efficiency of the solar concentrator. To calculate this, we consider the mass flow and specific heat of the water circulating through the heat exchanger driven by the pump along the energy provided by the concentrator meters. As a result, we obtain an average Tillman efficiency of 31%, which is quite favorable, considering that the system does not use a solar tracking mechanism. As for the efficiency of the dehydrator, we measure the mass flow of the air circulating inside the chamber, driven by the fan and a specific heat. During testing, we observe a water loss of about 1 gram every 30 minutes, which allow us to estimate an average dehydration efficiency of 26%. To conclude, this project presented the design, construction, and evaluation of an indirect solar dehydration system during an asymmetric solar concentrator. The system proved to be functional and efficient, reaching sustainable temperatures for fruit drying, with an average Tillman efficiency of 31% for the solar concentrator and 26% for the dehydration process. Tests with apples and other fruits, cut into small pieces, show that it's possible to obtain high-quality dry products with low moisture content and water activity in a reasonable amount of time and without the need for solar tracking. These results suggest that this kind of technology could be a viable and sustainable alternative for food drying, especially in regions with strong solar radiation like San Luis Potosí. And finally, here are some samples of the fruit we dehydrated using this system, which were later used for making tisane. Thank you for your attention.